Please welcome back Intel Fellow, Tom Petersen.
Wow. I'm back. And not just am I back, I love gaming. I've been gaming my entire life. I live for gaming. I still game, although I don't do as many like shooters as I used to do now. I'm kind of into the more city builder platformer thingies. Right now I'm playing a thing called Mindustry. Has anybody heard of Mindustry? Kind of an indie title. Yeah, back there in the back. Thank you. But I'm not the only thing back. Painkiller is back. We have a new version of Painkiller. It's exclusive here, preview courtesy of Anshar Studios. And I just want to start with what can we do with Panther Lake. So let's go ahead and run the game. This is a live demo of a new title. Kill!
This dark material is concerning.
Oh yeah, I remember this.
It's called construct. Used to fabricate purgatory and everything silent.
Oh yeah. Oh yeah. Yes. Get up top? Huh? All right, is anybody noticing up top there? That is our tool called PresentMon. We're killing monsters. This is fantastic. I love that demo, and we're going to have this around for you guys to play with. This is, again, real time, running on Panther Lake. What I love about it is it's running on a fantastic screen. This is 19 by 10. We have VSync off, and if you look in the top right, that is PresentMon. We're running at around 220 frames a second. That is using a new technology I'll talk about in a second. And I have another thing down below it called FPS app, and I'll talk about that in a minute. So those are two different numbers that are both important. All right, thank you for the demo. That's fantastic. Let's come back to the slides. All right, power efficient gaming. So that was all being run on a 44-watt laptop or a 44-watt platform, which is actually a reference platform back there. All right, so it's running live on pre-production version of Panther Lake. That game comes out October 21st on Steam, and it does include one of our technologies called XeSS-2. Does anybody remember XeSS-2? Thank you very much. Thank you. XeSS-2 is one of our technologies we launched with Lunar Lake, and it actually is a frame generation technology. It's very, very cool. And I'll talk a little bit more about that in a little bit. Okay, so what do we need for good gaming on a low-power platform? Obviously, we need a very performant GPU. We just talked about one this morning. We also need something called smart rendering. And smart rendering is going to talk about the transition that's happening in graphics engineering. And that is the conversion from traditional raster to much more of a hybrid rendering approach where AI is blended with traditional raster. And lastly, we are a platform. It's not just about the GPU, it's about the CPU and the GPU and the memory and the power levels and all that kind of stuff. So we need to do a much better job of being platform aware and also being application aware. And I'll talk to you about some new technology that does that for us. Okay, so we covered it in the morning. I want to recap it if you forgot. We have launched Xe3. Xe3 is our new core. It's got tons of improvements. It has got a 33% bigger L1, which cuts down on all the thrashing. We have a much better register allocation policy. We are delivering much higher IPC. We also have more threads in our Xe vector engine, enhanced ray tracing units that are more fully utilized, and we have better graphics fixed function hardware, better filtering, et cetera. It's truly a next generation IP, and you will see more from this as we go forward in time. I covered these micro benchmarks also this morning, but suffice it to say, on most things, as compared to Lunar Lake, you're going to see more than a 50% uptick in performance. So that's a spectacular user experience improvement, and you can expect it to be sort of generally across most titles. This is one frame. Okay, now I love this chart because it's showing you purple is Panther Lake and blue is Lunar Lake. So purple is 12 Xe3 cores, that's the purple, and Lunar is 8 Xe cores. So the way to think about this is every frame that we render is a series of API calls, DirectX, right? And they do things like loading textures and doing some computation and blending some stuff, and it's lots of calls. And as time goes by, time is the vertical axis. So you want to be lower. That means you're faster. But every platform runs the same API calls. So I want to highlight what's happening here. First of all, you'll notice that Panther is just generally lower. And that's mostly because it's a faster configuration, and it has IPC improvements kind of throughout the pipeline. So you would expect the trend of Panther to be lower. The second thing that you're going to see is in the beginning, there is a notable drop, a notable bump of about 2.93 milliseconds. And that is happening during this phase of processing called the render prepass. So in this phase, the graphics card is or the graphics engine is sort of setting up things. It's doing pre-renders. And we're taking advantage of our new 10-thread support on the core plus variable register allocation. So we get about 2.9 millisecond savings just from those two technologies. It's pretty cool. As we go forward in the frame, you'll see there's a place where we separate by another 0.39 milliseconds, and that is because of our larger L2. Going from 8 meg to 16 meg keeps more of our context closer to the GPU, which means we have less misses, less traffic to the memory. As you go forward, you'll see our variable register allocation click in again for 1.63 milliseconds, followed by a variable length register plus L1 cache improvements, delivering 7.8 milliseconds. This was the Achilles heel of our prior generation architectures. We didn't have enough capacity. We had a lot of register spilling happening, which sucked out some of our IPC. So variable register allocation, a larger L1, keeps all that stuff on board and helps us fully utilize the hardware that we're delivering. So that is a very cool way, I think, to kind of visualize microarchitectural improvements translate into real-world performance. In this case, the final answer is, what is that? That's about 45 milliseconds for Lunar and about 22 milliseconds for Panther. So it kind of lines up with our claim of around 2x performance. Okay, let's keep going. So that's a fast IP for graphics. We also need smart rendering, right? So smart rendering is all about changing the way you think about generating pixels. In this first picture, what I'm showing you is a visualization of rasterization. This is the way graphics have worked forever. You have an artist that will create a model. In this case, it's sort of like a weird blobby green thing. I don't know what that is. But anyway, you create a model, and then you project it down to your screen, which is just a mathematical multiplication of a matrix to convert it to two-dimensional pixels. And then you run a code for each one of those pixels that's aware of the environment and has a custom sequence to color those pixels based on the geometry that has been projected. Okay, so that's much of think of it like an artist painting a picture. The artist creates the model, the mathematics project the model to 2 dimensions, and then you color it using a program that an artist created. Now that has evolved, right? And it's evolved to hybrid rendering. Hybrid rendering is the same idea. We're going to generate kind of a base image using raster technology, but then we're going to augment that image using ray tracing. So things like reflections, things like shadows, things like ambient occlusion can all be dramatically improved by doing effectively a light simulation using the geometric scene in front of us and then augmenting that rastered image. I did a dedicated video just on this that helps explain the details. If you want, I'm sure you can find it. But hybrid rendering is kind of where we are for most titles today. But things have indeed moved forward, and we are now into the world of hybrid rendering plus AI. And in this world, not all pixels are rastered. In fact, most pixels are not rastered. They are generated. In this picture, I'm showing you XeSS in action, where we actually render to a smaller resolution using raster, but then we use AI to super sample that image. That's that small one going to the big one. And then even after that, we use frame gen to synthesize and create a new image between two prior rendered images. So this is showing you XeSS-2. And it's how we get great performance scaling on Lunar and Panther. Okay, now XeSS is interesting because all pixels on the screen that you see are generated. There's literally nothing rastered. Everything is upsampled and then generated. It's pretty cool. And it works pretty simply, right? We have a super resolution technology, we have a frame generation technology, and a low latency technology, all connected into this XeSS-2 tech. This is the way to think about it. With traditional rendering, on the top, I'm showing you fixed point and floating point operations, and on the bottom, I'm showing you operations in the geometric pipeline. So whenever you're rendering a frame, you do a complex combination of math on the top. In this case, in the beginning is when we're rendering the G buffer, which is sort of a kind of the beginning stage of rendering lots of things like a color and maybe a depth. And that uses geometry quite a bit. Then we're running a bunch of ray tracing. We do denoising, and then eventually kind of merge it all back together. This is what you would think of as a normal frame generated. This is actually F125 with ray tracing on. Now, when we invented XeSS-SR, it changed that a little bit. You can see in the front here, we're rendering quicker because that resolution is lower. So our generation of the G buffer is going to be very fast, and it takes less time to ray trace because the ray tracing image is smaller, there's fewer pixels. And then this purple thing pops up. And the purple thing is actually taking the low-res image and then applying our AI inference that we've developed internally to super sample that image using pre-trained knowledge about what do game frames look like. And so at the end, we generate this high-res image, and then we apply post to it. So we added our post effects, things like UI and other, and we get a frame. And that frame is as good as the prior picture, the native frame, but it's actually being run quicker. So you can see XeSS is about 30% quicker than the native resolution, and that's called AI hybrid rendering. It was our first attempt. Now, since then, we have moved forward and added XeSS-2. So now instead of just upsampling, we actually upsample, then we do a network to calculate what's called optical flow. So AI is looking at the two images that were rendered, and it's calculating what are the vectors that represent the motion that's captured by these two frames. And then we use that optical flow network to kind of synthesize the middle frame. Right? And what we're doing is we're saying, things are obviously moving, things are changing. What should be the middle frame? And we let AI calculate it. And you can see, again, now we're getting 2 frames. So instead of that first one where we got 1 frame, now we get 2 frames. And so the performance feels like it's roughly double. It's pretty cool. And you can see how short that time is to generate a frame. It's very, very fast. So today, I'm happy to say that we are introducing a new version of our performance application called PresentMon. Near and dear to my heart. My team actually works on this directly. And you can see what I'm showing you here in the middle is 3 numbers. One is called the green one, FPS Presents. By the way, this is the most used application worldwide for measuring gaming performance. It's used by every other tool integrates this to do game performance measurement. So it's got FPS Present, FPS Display, and FPS App. And what you can see is I say present is 225 and app is 55, which is roughly more than 4 times faster. So what's going on here is we're representing frame gen different from rastered frames, because we think that people are most comfortable with thinking about performance as what's my natural raster performance. So even when you have frame gen on now with our PresentMon tool, we'll tell you what your natural performance is, which is going to be whatever you raster at. So in this case, we're rastering at 55 frames per second. The 225 is frame gen. So that's telling you how many times did we generate a frame and what is the effective feel on the screen. But we are saying, hey, listen, this is complicated. It's emerging technology. There's been a lot of controversy about how to think about performance. So what we're going to do is we're going to quote native FPS performance, our raster performance, as our baseline performance for our graphics. But we're also going to say, hey, we do have these frame gen technologies, and they do improve the experience, and we'll give you another metric to kind of like cover that one effectively. Also in this version of PresentMon, we added 3 new things. One is frame time differentiation. So when you generate a log, you'll get a CSV that tells you whether this frame was real, whether it was app rastered or whether it was generated. And you'll also get a new metric called animation error. I talked about this in Taipei last time. And it's actually a better way to think about stutter. If you're into percentiles and all that kind of stuff, then this is the next gen of that. And what it's actually measuring is animation stutter on the screen. So if you're out of sync in terms of the rate that frames are being generated or the rate that things are showing up on your screen, it'll show up as this new animation error metric. So that's PresentMon. Now, I'm excited to introduce our latest technology, XeSS-MFG, multi-frame generation. And you can see this builds on our prior generation, where effectively we're taking 2 prior render frames, we're generating optical flow networks using motion vectors plus the depth buffer, and then we're going to generate up to 3 frames between the 2 interpolated frames. And it's a very cool technology. It improves the experience quite a bit. But again, we're going to separate XeSS-MFG performance from our base raster performance. You like that? Here's a little animation. Thank you, thank you, thank you, thank you. I actually think that's pretty important because it's caused a lot of confusion. We're trying to make it simple. This is an animation of how MFG works, or how FrameGen works. You can see that we've got a frame that's rastered on the left and another frame that's rastered on the right. And then when those 2 come together, then when they come together, we get a generated frame. So we're looking in the future and we're looking in the past. We're pulling those 2 frames together. We're generating an optical flow. And then we're synthesizing that interstitial frame. We're using frame pacing on the output so that those frames show up at the right time on the display with no animation error. So you can think about that tech as MFG. With multi-frame generation, we are just actually up in it a lot, right? So we're now generating up to 3 frames in the middle, which gives you up to 4x the expected, the kind of the perceived performance, which means things are just cranking, cranking, cranking. As a matter of fact, this was on in the opening demo. Okay, so I told you this is what it looks like with XeSS-2, where you see that optical flow in the frame gen over there. With XeSS-3, it's different, but it's similar, right? We now do 3 blobs instead of 1. So we're kind of starting over here. We're doing the super res. Then we're doing an optical flow calculation, which is like the motion vector. Where should I put this? We're using that one optical flow calculation to interpolate 3 times. So kind of like 1/4, 1/2, and 3/4 of the distance. And that gives us just great looking frames. And that gives you the experience of smoother gameplay. So to really feel this, I'd like to pull up a demo. We're going to focus on multi-frame generation. What I'm going to do is show a game live running MFG. We'll put the PresentMon up so you can see app frames and presented frames. And then I'll slow it down, and we'll talk a little bit about what you're looking at, okay? But first of all, this is Dying Light the Beast from the developer Techland, and we're going to kill some zombies. So kill zombies. Kill zombies. Yes. Yes. Kill zombies. Zombies. Yes. Yeah. Brand new title. I love the game. I mean, killing zombies is always going to be fun. You can see the frame per second at 136, and the FPS is rendering at 33. So I want you to think about what you're looking at. This is a game that's rendering at 30 frames a second. But it doesn't look like it at all. Yes. All right, that's enough zombie killing. That's fantastic. So let's go to the next step, which what I want to do is I want to slow this down. Okay, now I can't slow it down in real time because games don't work like that, at least not yet. So I've done a movie capture. Okay, and we're going to capture it, and we're going to show you the movie, and then we're going to show you left and right slowed down by 4x. Well, let's go ahead and go to the movie. Okay, so what you're looking at is MFG on the right side and FG off on the left. The native render rate you saw is about 50 frames a second. This is slowed down 4x. Now watch that tree, right? You're getting, this is what happens when you watch a game that's rendering at a low frame rate. You get these like gaps in animation. It's very jarring. On the right-hand side, this is the experience of the AI-generated smoothing frames, right? The ones that we call presented frames. So it actually delivers a very, very smooth experience. But again, they're different. The frames are not really the same as the rastered frames, and that's why we separate them in our performance measurement, and we're going to separate them in our performance claims. Okay, what you're looking at is the XeSS FrameGen override control, and this is showing you our control panel. This will be available with Panther Lake as well. It's called Intel Graphics Software, and you can do all the normal things. You can control like AA, you can control the VSync modes, you can control a bunch of stuff. There's a new option in there that tells FrameGen how many frames do you want to generate interstitially. So you can do 2, 3, or 4. Who knows where we're going to go with this? This technology is really just at the beginning. But the cool thing is if you look closely, you'll see there is kind of a weird option number 2. See that number 2 option? It is actually talking about shared memory overrides. So at the same time we're launching this XeSS-MFG, which we're going to call, I think, XeSS-3, we're also including this shared memory allocator. So depending on if you're a gamer or not, you can shift memory from system memory to the GPU and vice versa, and can dramatically improve gaming on Panther Lake. All right. So that is smart rendering. We talked about a high-performance GPU. Now let's talk about platform tuning, right? And the idea is when you're gaming, it's important that the GPU and CPU know about each other and you know about the workload so that you don't do crazy stuff. Back in the day, we in fact did crazy stuff. This is showing you what Lunar Lake looked like at launch. This is just one title showing a bunch of these up and down. This is a frame time chart. And you can see these little spikes represent bad experiences, little stutters and hitches. It's been the bane of my existence as a graphics engineer for years. But we are tackling it because the source of those stutters is actually not anything happening on the render pipeline. It's not like new textures getting loaded or shaders getting compiled. Those stutters were coming from CPU and GPU balance incorrectly. Right? The algorithms for CPU and GPU balancing were fighting each other, and we're taking power from the GPU, we're taking power from the CPU, we're doing it too fast, and things are sort of oscillating. This other bar down here, which you may have seen going very, very slowly, is related to loading games. So at the same time we were stuttering, we also had slow load times. But I'm excited to say we've fixed both of those. First, to improve load times, we've moved to a precompiled shader structure. So Intel now has a cloud that is looking at games. And as games rev, we are compiling all of their shaders ahead of time and putting them in the cloud. Then our Intel graphics software is looking at the games that you're playing and automatically downloading precompiled shaders to your PC. So you don't have to wait for games to load shaders. You don't have to wait for stuttering in the middle of your level. All of this stuff is automatically managed by Intel and delivered to every client. So it's pretty cool. And you'll see that in Intel graphics software. You can turn it on and off. So if you want stutter and you want long load times, turn it off. Feel free. But if you want those stuff to be fast, leave it on. It'll make your life better. It reduces stuttering on first launch, so you won't see this like hitchy stuff. And it also does automatic updates as shaders change or games change or our driver changes. Pretty cool. The second thing we're talking about is power sharing. So if you think about the problem we have here, this is showing you GPU power, CPU power, and other. Blue is CPU, purple is GPU. And what's happening is all these spikes are showing, this is a power consumption. So all of these spikes are our microalgorithms running very, very fast, trying to optimize performance, but missing the idea that this is actually a game. So the fact that we didn't know that this was a game led to a lack of awareness, right? We didn't know exactly how to optimize. So we would cause CPU frequency spiking. Right, our frequency on the CPU would spike up, and then our GPU frequency would spike down, and that would lead to performance reduction and stuttering. Okay, so this is bad. We don't want to do this. Makes me sad just to see it. So what we're doing now is better. We are introducing, or we've already introduced, something that we call Intelligent Bias Control version 2. It's a typical Intel name. It's pretty cool. Maximizing performance efficiency for gaming workloads, okay? So it was first released in Q2 25, and this is available now today on Lunar Lake. And what's happening is inside of the GPU driver, we're looking at a couple heuristics. We're looking at whether or not there's a game playing. That's kind of a critical thing. We're looking at the GPU utilization. So is my GPU pegged? Am I really wishing I had more power on my GPU? And then the driver actually makes hints to our firmware, that rush we talked about this morning. And those hints are converted into hints to Microsoft to adjust the scheduling and adjust the use of our cores. So all of this reduces the stutter by dramatic amounts, and it improves performance. Okay, if you look at this on Lunar Lake, you'll see that we've improved performance by over 10% on average, and we've improved the percentiles, which is like the times that frames stutter, by more, right? This is showing you 31 to 55 frames per second as an example in the middle there on payday for just this one technology. And in terms of experience, that is night and day. So we've already made a big jump. It's 10% more FPS on average and 25% better lows. So those lows lifted up by 25%. And this seems kind of obvious, but it's very complicated. And it's now involving application awareness inside of our driver. Okay, so we're taking the second step into Intelligent Control version 3. And you'll see now, not only do we look at GPU heuristics and we look at the application environment, we're also looking to soften the transitions. So there's a new PID controller, which is a smoother algorithm for shifting between GPU and CPU power. And we're now doing E-core first scheduling. So when we're running a game, we're going to tend to schedule the game threads on E-cores first, thanks to all that logic that Rashri talked about this morning. The driver's job is to inform that algorithm that we're playing a game and that we need more power. The results of this are pretty spectacular. And if you look at Panther Lake, you'll see life is much, much better. Same game, different power, but roughly the same power. You can see how the spikies kind of level out there. But the purple is a lot bigger. We're giving a lot more power to our GPU. Thanks to the E-cores on Panther Lake, we're able to reduce the processor power and get actually much, much better performance. So Panther Lake optimized power delivery with platform tuning. Okay, so that's gaming. We have a new high-performance IP, Xe3. We have smart rendering with XeSS-MFG, where we can now render up to 3. By the way, the cool thing is the API for this to games is unchanged. That means if you have an XeSS-2 title, that all of those titles, when we release Panther Lake, will support XeSS-3. So that's super cool. And lastly, we've improved our platform tuning quite a bit, and you'll see much smoother games for all of our gamer delight. And with that, thank you very much for your attention. I'm happy to welcome Dan Rogers to wrap it up for today, and we'll meet you outside.